All right, so what we're going to do now is we're going to look at the derivatives of exponential functions. And we will see that they have a very, very cool property. We'll see this as soon as I find what I just did with the pen, which I literally had 2 seconds ago. How do I manage to lose pens at this kind of rate? Well, this pen is sort of working for now, so we're going to roll with it. So I want to think about taking derivatives of exponential functions. Now, suppose that I want to take the derivative of a to the x, where a is bigger than 0 and a is not equal to 1. Let's go ahead and write down what this would be in terms of the limits. Well, this would be the limit as h goes to 0, a to the x plus h minus a to the x, all divided by h. So what is this going to be? Well, this is going to be the limit as h goes to 0. I can factor out an a to the x here, and I can write this as a to the x times a to the h minus 1 divided by h. Make sure that you see what I did here. I'm just factoring out an a to the x here, and I can do this because of the laws of exponents. So what is this going to come out to be? This is going to come out to be, I'm taking the limit as h goes to 0. So for the purpose of this limit, a to the x is just a constant. I mean, a to the x depends upon x, but x isn't changing here. X is fixed. We've fixed x. So this is actually a to the x times the limit as h goes to 0 of a to the h minus 1 divided by h. Now, this is really, really cool. Why is this really cool? Because what we have shown is that the derivative of a to the x is a to the x multiplied by something which does not depend on x. Like, this is literally just going to be some number. Assuming that it exists, this is just some number. And therefore, the derivative of a to the x is going to be some number, some constant number, times a to the x itself. That means exponential functions have the special property that their rate of change is proportional to their value. And this is a property which is so common in nature and in applications, okay? There are so many things that their rate of change is proportional to their value. In physics, nuclear decay, the rate at which a radioactive material is decaying is proportional to the amount of the radioactive material that we've got. If we're thinking about in physics something moving under the action of friction, the rate at which it is accelerating or decelerating really is going to be proportional to its velocity. So the rate at which the velocity changes is proportional to the velocity. In medicine, the rate at which the body processes out toxins is proportional to the concentration of toxins in the bloodstream. Roughly speaking. I mean, of course, there's like some slight variation there, but it's approximate. Similarly, in biology, if I have a population of animals, I guess this is more ecology than biology, but a population of animals, well, the rate at which the population is changing is proportional to the population. At least if there's no like limiting factors in the environment, like a lack of food or something. Assuming that there's plenty of food to go around, then the overall rate of change of the population is proportional to the population. In financial mathematics, the rate of interest on an investment is proportional to the investment. Or, well, not the rate of interest, but the amount of interest you're getting is proportional to the investment. So, this kind of property, the fact that the derivative of an exponential function is proportional to that exponential function, this is really, really cool. The only thing we have to establish to finish this off is that this limit actually exists. And that is going to be our task for the next few minutes. Now, if you don't follow everything in this argument, that's okay. I am going to say a few things in this argument that we have not quite talked about yet. So one of the things that I'm going to mention is that if a function has a positive derivative, then it is increasing. And if it has a positive derivative everywhere, then it is everywhere increasing. That's intuitively obvious, but we haven't quite established it yet. So there's a couple of things that we're going to establish later. And once again, there's not going to be any circular reasoning. It's just we haven't established these things yet, but we've kind of intuitively talked about them. So here is the argument to show that this limit actually converges to a number. And so let's focus in on that limit. And let's see if I can follow through the notes that I made here. So let's let m of h be equal to a to the h minus 1 divided by h. In other words, it's the thing that we are interested in here. What we need to establish is that this thing has a limit at 0. So the first thing that I want to observe is that m of h is continuous for h not equal to 0. That's pretty obvious because exponential functions are continuous, and this is just arithmetic operations with exponential functions and a polynomial in h. So the only possible problem that we will have is at 0. And we don't actually, like, it's undefined at 0. So, you know, that is not like that. It cannot be continuous at 0 because it's not defined there, but it is continuous on its domain. Now, the next thing that we're going to do is we're going to need to make use of the power rule for rational numbers. And we're going to show that m of h is increasing on rational numbers. So here's what I want to do. We're going to fix r and s, rational numbers, and we're going to do 0 less than r less than s. It's a similar kind of argument to show this is going to establish that this function is increasing for positive h. Showing it for negative h is very similar, so we're just going to go through the positive case. And now I'm going to define, and this is a very clever trick. I did not come up with this trick. I'm going to define a function of a, g of a, to be equal to m of s minus m of r. Then the derivative of g with respect to a is the derivative with respect to a of a to the s minus 1 over s minus a to the r minus 1 over r. And we can establish the power rule for rational numbers without needing to know how to take the derivatives of exponential functions. In fact, we can do it for real numbers in general. So the place where I got this argument from, they just do it for rationals and then say, therefore, it's also true for the irrationals. So we only really need it for rationals here, but it doesn't really matter. Applying the power rule here, we end up with, let me make sure that I'm telling you the truth here. This simplifies down to s a to the s over s minus r a to the r over r. The s's cancel, the r's cancel, and we get a to the s minus a to the r, which is going to be bigger than 0 because s is bigger than r, and we know exponentials are increasing. Oh, and I should say here that we're going to take here a to be bigger than 1. If a is less than 1, then this comes out to be negative, m of h is decreasing, and we flip our arguments around. So it's the same kind of argument, just in the reverse direction, like all the inequalities end up getting reversed. And what this establishes then is that since we know g of 1, we can calculate that to be 0. So g of a is positive for a bigger than 1. And this establishes that m of s minus m of r is bigger than 0 for a bigger than 1 and s bigger than r. And this means m is increasing when h is bigger than 0. Now, we can go through the same kind of argument to show that for h less than 0, it's also increasing. So a similar type of argument will establish this. Now, that was quite the roundabout way of doing things. But there we go. We've got this established now. So what do we want to do next? Well, the next thing that we want to do is, now that we've established that m of h is increasing, we want to go ahead and say for h bigger than 0, m of minus h is equal to a to the minus h minus 1 over negative h. But this is actually 1 minus a to the minus h divided by h, which is equal to a to the h minus 1 over h times a to the minus h, which is m of h a to the minus h. There we go. This means 0 is less than m of negative h, which is less than m of positive h. And that means that 0 is less than m of h minus m of negative h. But if you calculate what this becomes, this is actually m of h times 1 minus a to the minus h. Now, taking the limit as h approaches 0 from the right, m of h times 1 minus a to the minus h, this is going to have to be equal to 0, because this term here goes to 0, and this does not blow up to infinity. But then, by the squeeze theorem, or sandwich theorem as it's known, this means that the limit as h goes to 0 from the right of m of h minus m of negative h is equal to 0. So, what this establishes is that the limits of these two terms here have got to be the same. They both have to be approaching the same number here. And since they end up approaching the same number, one of these is m of h, one of them is m of minus h. So one of these is the limit from the right, the other is the limit from the left. This establishes that the limit from the right and the limit from the left are actually equal to one another. But m of h is actually the quantity that we are interested in. It is actually this a to the h minus 1 over h. And if the left-hand limit and the right-hand limit both exist and agree, then the limit exists. And so what we have established is that the limit as h goes to 0 of a to the h minus 1 over h exists. And now, give me a second here because I am worried about one more thing. Oh, yes, right. So the only exception would be if these things blow up to infinity or something. But these are bounded functions, so they cannot do that. And they have to be bounded because we established that they are increasing functions. Where did we establish that they are increasing? Yeah, we established that a minute ago. I was just checking my notes to make sure we really did this. So because of this, they have to be bounded, and therefore this can't be some weird infinity minus infinity kind of thing that cancels out. So in other words, this really does have to exist. Okay, sorry. Just making sure that my notes were actually complete here. So don't worry too much about this proof. Again, if this were an analysis class, I would insist that you guys be able to do this in detail and we'd be much more careful about this. But I just want to show you that, yeah, we really can establish that this limit exists. Now, there's one more thing that we want to be able to do. We want to be able to say, what is this limit? So I'm going to post a paper, the paper where I got this argument from, which will show you what else we can say about this limit. Well, it turns out that we can actually make this limit be equal to pretty much whatever we would like, at least as long as it is bigger than 0. And that's a rather nice feature. So because of this, since we can make it equal to whatever we want, we define the constant e by saying it is the number for which the limit as h goes to 0 of e to the h minus 1 divided by h is equal to 1. And as I said, we haven't established that there is a number for which this is equal to 1. We've established that this limit exists, but we haven't said what it could be equal to. Well, it turns out that it's not too difficult to see. Once you get that you can make it equal to something, then you can kind of rewrite any of the others to be equal. You can end up showing that, yes, there has to be a number for which this limit is equal to 1. And if you want the details on that, you can look in this paper. Again, this is not an analysis course. We're not going to go quite that in-depth here. This is literally where the definition of E comes from. Now, you may have seen some other definitions of E before. They end up being equivalent to this definition, but this is the easiest one to start with, and then we show that all of the other definitions of E are consequences of this one. So, one of the results of this is that the derivative of e to the x, well, this is equal to e to the x times the limit as h goes to 0 of e to the h minus 1 divided by h. But we defined e by the property that this limit is 1, so the derivative is just e to the x. And therefore, the derivative of e to the x is e to the x. The derivative of this function is itself. And this is why e to the x is so special. This is what makes the number e super special and why it shows up all over the place. It is the number where, when you use it as the base of an exponential, it comes out to be, the derivative, I should say, comes out to be the original function. Now, later on, we're going to see how we can use some other rules for derivatives, and we'll be able to compute any derivatives that we want in terms of this fact, and that will help us to see what all of the other derivatives of the exponential functions are. So we'll come back to the other exponential functions, but for now, this is the rule that we want to remember. The derivative of e to the x is e to the x. So of course, we can put this together with the other rules that we've had so far, and we can do things like, what if I want to compute the derivative of 5x squared minus 3e to the x? Well, the derivative of 5x squared is 10x, and this is going to be minus 3 times the derivative of e to the x, but that just remains minus 3 times e to the x. And there we go. That pretty much takes care of everything we need to say about that. We're really kind of done there with the exponential, at least e to the x. Like I said, later on, we'll see how to deal with exponentials using other bases. I mean, I can go through more examples here, but literally it's just the e to the x derivative is e to the x. So all the examples are kind of the same. Now, what we're going to do is we're going to make use of this in the next lecture together with the other rules that we see to get some much more interesting examples going on here. So don't worry, we will see more interesting examples coming up here soon. But for now, I think that's all I really wanted to say to finish this off. And also, you've got the test coming up this week, so I'm going to try to keep my lectures a little bit shorter this week than usual, so you have some extra time to work on that and prepare for it. So I'm going to stop this here, and we will return with more rules soon.